Hey everyone, welcome to two-dimensional kinematics relative velocity example 2. A boat can travel 2.03 meters per second in still water. A. If the boat points its prow directly across the stream whose current is 1.02 meters per second, what is the velocity, magnitude, and direction of the boat relative to the shore? And B. What will be the position of the boat relative to its point of origin after 3.03 seconds? Now, I'm going to solve this problem using the same ideas as the ones in example 1, but I'm going to solve it a little bit differently. Instead of using x and y components, I'm simply going to show you it in terms of the picture and how to solve it just based on that. The steps are very similar. The only difference is I'm not going to separate the vector into x and y components here, just so you can see that there are two ways of solving these types of problems. So, this question did not come with a picture, so I'm going to go ahead and draw one for this one. So you've got a stream. A lot of these questions are very similar. You've got the stream and the person is going across the river, but in fact the current is going downwards. So the relative direction is going to go a little bit on an angle. Okay, now before I actually draw in any vectors here, I need to establish my three objects. Okay, so in this question, my three objects are going to be the boat, the water, and the shore. Now I need to abbreviate these as well with the letter. So boat will be B, water will be W, and shore will be S. Okay, now in terms of what we're given a boat can travel 2.03 meters per second in still water. You'll notice that in the previous question, the previous video, number 48, we were told, you know, the boat's moving relative to the water. But in this question, they don't tell you that language. They don't use that language, but you have to understand that the boat traveling 2.03 meters per second in still water means that's the velocity of the boat relative to the water. So that's B relative to W, and that's 2.03 meters per second. And now, the other thing they tell you is that the stream has a current of 1.02 meters per second. That is the velocity of the water relative to the shore. So 1.02 meters per second. Okay, now let's establish our positive directions. It is a two-dimensional problem, so I'm going to let positive be up and to the right. Again, see video 48 if you want to learn how to do it using x and y components. In this video, I'm going to solve it a little bit differently, although you'll notice that the math comes out to be almost the same. Okay, so now we've got boat relative to water. Now this is the boat actually trying to advance across the river to the other side, whereas the water is going downstream. So you're left with vectors that look like this. You've got velocity of the boat relative to the water across, and perpendicular to that you've got the velocity of the water relative to the shore. And when you add those up, you're going to get a resultant. Now, let's just check this out. The question is saying in part A, what is the velocity of the boat relative to the shore? So we're looking for VBS. And if you take a look at those subscripts, you've got BW and WS. Remember, back to video 48, we talked about how we come up with the expression. So if you're looking for VBS, okay, you start by writing down your two V symbols. Now the first letter you see here, the B, is the first subscript of the first V, and the second letter S here is the second subscript of the second V. Now you fill it in with the remaining letter, which is W. So VBW plus VWS, and those are exactly what we're given in the problem. So at this point, we simply need to plug it in. So remember, according to rules of relative velocity, the inner two letters should cancel out. Okay, leaving you with the outside two, which is exactly what we're looking for. Okay, so let's go ahead and solve this problem now. Let me shift this up a little bit. So we've got VBS is equal to VBW plus VWS. Now notice something based on the picture. If you recall in the previous video, we added the magnitudes by taking the sum of the squares of the two sides which were not the hypotenuse. If you take the sum of these two squares, you're essentially you're using Pythagorean theorem. You're trying to find the hypotenuse of this right angle triangle, and you've got the two other sides. So in order to find the magnitude, we're going to do exactly that. We're going to use Pythagorean theorem. So VBS is equal to the square root of the sum of the squares of the VBW squared plus VWS squared. Let's plug in our numbers here. So VBW, the boat relative to the water, that's 2.03 meters per second. You square that. And add to that the water relative to the shore, 1.02 meters per second. Square that. And so VBS, if you take the sum of the squares and you square root the entire expression, you'll get 2.27 meters per second. Okay, now to find the angle, okay, so looking back on the diagram, for the angle, you're looking for the angle between the hypotenuse and the initial vector there. So that's our theta. Since we're given VWS and VBW in the original problem, we want to use those in our solution. So what we're going to do is use a tangent, tan of theta. Okay, so we're going to say tan theta is equal to VWS over VBW, which is equal to 1.02 over 2.03. Okay, that ratio comes out to be, so tan theta equals 0.50246. In order to solve that, you take the inverse tangent of both sides. Okay, so when you do that, you're going to end up with 26.68 degrees. Of course, too many values there, so we're going to round this to 26.7 degrees. So theta is about 26.7. Now here's the thing. In the previous video, number 48, we expressed our angle relative to the shore. Okay, but in this problem, our theta here, I mean, what is it really relative to? It's not really relative to the shore. It's relative to this vertical line here. And expressing an angle relative to your first vector, it's not helpful. What we're actually going to want to express our angle relative to is the shore, like we did in the previous video. So that's going to be this angle here. We'll call that alpha. Okay, and if you look, alpha is simply, like alpha and theta together add up to 90 degrees. So if you simply subtract theta from 90, you'll achieve alpha. Okay, so that's what we're going to do here. We're going to say alpha is equal to 90 minus 26.7. And when you do that, you're going to get alpha is equal to 63.3 degrees. And so there you have your angle. This is relative to the shore. You've got your magnitude, 2.27 meters per second. Okay, so therefore, the velocity of the boat relative to the shore is VBS, and remember to put that arrow on top, which is equal to 2.27 meters per second, square bracket, 63 degrees relative to the shore. So there is your answer for part A, okay, to find the velocity relative to the shore. So not too bad. We have one more part left. This part is a little bit shorter and more straightforward. Part B asks again, what will be the position of the boat relative to its point of origin after 3.03 seconds? Okay, so after 3.03 seconds, based on the original problem, take a look here. Okay, after 3.03 seconds, it's going to be downstream by a certain amount, and it's going to be across the river by a certain amount. Okay, we don't want to simply express it as, okay, it's this distance away or this many meters away at this angle relative to the shore. We're going to say, well, the boat ended up X meters downstream and Y meters across the river. Okay, so that's how we're going to solve part B. So let's just dive into that right away. So for part B, let's figure out the amount downstream that the boat ends up. So this is a simple kinematics problem at this point. Distance is given by speed times time. There's no implication or even assumption of acceleration in this problem. So we're going to say, so distance is equal to speed times time. So the distance is going to be the distance downstream, so I'll just call it d sub d. The speed, well, why are you ending up downstream in the first place? You go downstream because of the current, right? And based on the problem, we define the current to be the water relative to the shore. So the V here is going to be VWS. Okay, so let's plug it in. So VWS is 1.02 meters per second, and it asks us relative to 3.03 seconds. If you multiply the two of those together, you're going to get 3.09 meters. So the boat's going to be 3.09 meters downstream. Now, how about across the river? Okay, so they ran across the river, so we'll call it dA for distance across. Same formula, speed times time. Time is universal, you don't need to give it a subscript. Okay, the speed in this case is the boat relative to the water, since that is what gives it its tendency to go across. So VBW is equal to 2.03 meters per second times our time, 3.03 seconds. When you multiply the two of those together, you get 6.15 meters. And after this, there really isn't much more to this part of the problem. Okay, so all you have to express is this. Okay, so therefore, the boat will be 3.09 meters downstream and 6.15 meters across the river. And that is, of course, after 3.03 seconds. And there is your answer for part B. Okay guys, that's it for this video. If you enjoyed it, please click that like button and subscribe to Physics in the Flesh so you never miss a video from me. I will be posting more relative velocity examples, so be sure to check out my latest videos as they come out. Enjoy the rest of your day guys, and I will catch you in the next video.